Welcome, Math 170. Today we're going to talk about functions. Just want to let you know that most of Chapter 1 involves concepts that they expect us to pick up from our algebra and trig classes or pre-calculus classes. We won't be covering the entire chapter in great detail, but I definitely will touch upon some important stuff that you'll be needing along the way. And then I just encourage you, if you are confused about anything, just please message me in Canvas or set up a tutoring appointment with the Success Center or our embedded tutor, and we can help you fill in those gaps. So starting on section 1.1, just want to kind of go over the 4 ways we're going to represent a function. And a lot of times we haven't used this in a while, but we're looking at representing functions verbally, and pretty much what we mean is we're looking at expressing functions using words. And an example would be maybe everyday life. We don't necessarily think about this in math, but the hours worked versus our total pay can be an example of expressing functions in words. And let's see, going on to the second content, numerically, you may see a function represented as a table. And I don't know if we've done this in a long time, but some of you, when we were graphing lines or other particular functions, we would use an XY table to help us plot the points. Or sometimes that will relate to data points. So we'll see that a little bit later in the examples so that we can go through that. Visually, kind of goes along with numerically. You will see that we can express functions through graphs. And sometimes that is more valuable because you can see the behavior, whether functions are increasing, decreasing, and so on. And algebraically, if we're looking at expressing a function, sometimes you'll see us write out a formula. No stranger to math there. And an example for that, we can give you kind of a trig graph. I'll throw that back into the class. If we have a cosine function shifted up 3 units, it's kind of representing a function. You could also talk about it if you're playing with some of the introduction examples that we were talking about earlier. We're looking at the area of an equilateral triangle. As a function of its side. So if you were playing with some of those examples earlier, you kind of came up with an expression to help you solve that problem. So just so that we kind of can make the connection with functions, a lot of times in this course, we're going to talk about these being represented with pictures. So a little bit visual idea. I have a graph of a function. We don't know the equation of it, but we do know the behavior. And it kind of reminds us that when we talk about ordered pairs, I'll kind of write it on this graph right here. If we're looking at this point, a lot of times we're looking at an X and Y value. But when we talk about function and function notation, the Y ends up being denoted as f of x to give us a heads up that we have a function in line. So we end up having our x values and our corresponding y values written as ordered pairs or in function notation. So you can kind of see that the second point I am plotting right here is the function evaluated at 2. And then any general point along the function is what's happening when you're looking at the x value, what is the corresponding y value? So x, comma, f of x. Another thing to remind ourselves about functions is that we like to talk about all the possible x values and all the possible y values when we're viewing the picture. So just kind of reminding us that we talk about this in terms of range and domain. And domain, just a quick reminder, is all the possible x values. Of a relation or a function. And then the range, to remind us, is all possible y values. And a lot of times when we're looking at reading our graphs, a lot of times I'll remind you that if you're looking at the domain, you travel along the x-axis and then you try to determine if there are corresponding y values for every x value you're moving along with. And we see that that's happening right here with this generic function. And similarly with the range, you would travel along the y-axis and try to determine for every y value, do you have a corresponding x value? It's kind of a nice visual way to speak about domain and range. So to start off with our first example, I've graphed, or I have a picture of a nice graph of what they call f of x, our function. So sometimes we like to label it to help ourselves remember this. And this is kind of another way to talk about function notation. Instead of knowing what the formula is or the algebraic representation of the function, if they want us to find f of 2, that's actually telling us to go where 2 is located on the x-axis. And so when I look at my picture, I see that the labels on the x-axis, it looks like they're going by ones. So I can assume at x equals 2, should be right here, I would want to travel to find where my corresponding function is. So this looks like I'd have to look upwards to find this result. So I've just drawn a picture or a point of what f of 2 is, but we like to consider what's the actual y value. So that would mean that we can look back on our y-axis and count to see what that value is. So we can label it, yes, as f of 2, but really, let's see if I can write it a little bit better for you all. Well, I'd like to erase that for a second. There we go. I can definitely label it as f of 2, but I want to know the actual number. So if I count 1, 2, 3, 4, that is actually going to be the value of the function when x is equal to 2. So that's kind of another way to talk about the point or ordered pair 2, 4, just to kind of refresh your memory. And let's see, if we look at f of 7, I'm going to count all the way to 7. So I have 1, 2, 3, 4, 5, 6, and 7. And it looks like the function is actually right on the x-axis. So if we were to look at that ordered pair, that's actually called 7, 0. But when we talk about function notation, that would be the function evaluated at 7. And again, that would be where 0 is. Now, if we want to talk about the domain of f, we want to make sure that we know, is this a continuous function or is there a starting or stopping point for our x values? When I look at this example, I'm seeing that the function has definite starting and stopping points. And when I read for domain, I just want to remind myself that I am looking at the x-axis. So let's see if I can clean this up a little bit so that we can really see what our particular function leads us to. So I'm going to erase a little bit just so we have a cleaner picture. And if I am looking at the domain, I'm going to look at the x-axis. And when I look at the x-axis, I want to determine, as I'm moving along the x-axis, I'm looking for a picture above, below, or on the x-axis. And notice as I'm kind of marking areas on the left side, negative values of x, I notice if I look up or down, or even on, I do not have a picture of the function. So there's nothing happening until x equals 0. And once we hit x equals 0, every x value from 0 until 7 is going to give us a corresponding y value either above, below, or on the x-axis. So we can describe the domain in interval notation as all the values between 0 and 7. And then when we're using interval notation, just a reminder, we're using brackets to indicate that the 0 is included because we do have a clear function value at x equals 0. And also the 7 is included because we have a clear function value or y value at x equals 7. Interval notation is also representing all the numbers in between, not just the integers. So we're looking at all the decimals and fractions as well if we're dealing with the domain. Now, if we want to talk about the range of f, I'll clean up our picture one more time, if I can. Let's pull out the eraser, make this a little bit easier for me. So one more time, if I'm looking at the range of f, I now have to look at the y-axis. And a lot of times what I tell everyone is I like to start off at the lowest possible value of y and see if I have any picture to the left or to the right. So I notice for this y value, the very smallest y value on my coordinate system, it looks like it's at -3. There is no picture to the right or to the left of my function. So I keep traveling until I can kind of see if there's a picture. And we're assuming at this point there's no holes. So it looks like at y equals -2, we have a corresponding x value for that y value. And we can kind of judge. All of these values seem to be to the right of our particular y value. But as I travel, I can see that I'll be looking at going from 2, or -2. And just as I can see, I keep looking at particular y values and I keep seeing pictures. In this case, we have 2 x values. And we can travel all the way up until y equals 1, 2, 3, 4. So we notice that we have the last particular y value. So the range would be described, and we can do interval notation as, again as -2 to 4 and all the numbers in between. -2 and 4 is included because we actually have function values at those points. And just kind of an exploration here, if you were to go beyond 4, you'll notice that you no longer see a picture to the left or to the right of your particular y value. So that's a clear indication that your range is finished. So hopefully that helps out with some of the WebAssign homework in this section to help you out with identifying, making the connection between the function values, range, and domain. Now, another example I'd like to show you, we're going to look at example 2, and we're going to bring back what we call piecewise functions a little bit, just to give you guys a heads up. This is considered a piecewise function because it is broken up into 2 or more parts. Now, when we look at graphing piecewise functions, a lot of times what I tell everyone when they're first starting is just consider the function, each piece separately. And sometimes I just graph them as if I were to ignore the fact that it had a domain at first. So to start off, I'll take the positive case of the x. So if I look at a function, and I know f of x is another way to say y. So what if I looked at this? And if I can remember clearly, that is a linear equation. And if I were to graph it, it's a quick little mini graph on the side. If I were to compare this to y equals mx plus b, my favorite version of the linear equation, I can see that my slope is 1 and my y-intercept is 0. So if I were to play with graphing it, a quick accurate graph, I can start at 0 and travel rise over run, up 1 over 1, up 1 over 1. And if we connect, we could kind of see that we have a line, excuse my non-straight line, but we don't have a ruler at this time. But we can see that that's the graph of a linear equation. So I like to graph it as if I just saw it without the piecewise and without the domain. And what I'll do later is I'll then kind of address the domain. It looks like for this particular piece, they're describing that the domain is all values of x greater than or equal to 0. So if I'm playing with that idea, what I'd be looking at, I kind of go back to the idea of a number line, one-dimensional. I'm going to look at the x-axis, and I will kind of highlight all the x values greater than 0. And that's everyone to the right of the origin. And what I want to deal with is I want to see what corresponding y values are made for those x values, any of those x values in the highlighted region. So I notice I would have to look upwards to find my corresponding y values. So that would indicate that I would not need this piece for all the x values that are less than 0. So you would see that I would erase it. And the way I erase things sometimes here is I'm crossing it out in red. I can also erase it if it'll let me. You can kind of see if it will go. There we go. So if I do that, what I'm kind of going with, I can actually translate that to my formal graph. And that piece right there, if I'm now fully writing it out, if I got to remember, if I'm looking at the very end of the function, and let me draw this one more time just to make sure. A lot of times the domain's going to cut the function at a certain piece or place. And at this point, it cut it at x equals 0. That would be kind of the indication of we'd have to decide, do we want an open or closed circle at that part? And it looks like based on the inequality symbol, since we have a greater than or equal to symbol, we would use a closed circle or a point to help us mark the edge of that function. So if I'm going to graph that piece on my formal graph one more time, I can start off with a closed circle, use the slope to get to the next point on the line, up 1 over 1, up 1 over 1. I can be as accurate as I want. If I don't have a straight edge, I like to sometimes use the slope to my benefit. And then I will draw my function. Now, it doesn't always end at 5. It goes on forever and ever. We're going to remember that. So that is one piece of the function. If I want to draw the other piece, see if I can give you another color code. I'd like to look at the top piece, f of x equals negative x, or another way we would say y equals negative x. And I'll draw that. And just kind of remembering, if we have a little bit of knowledge from our past with linear equations, the slope is -1, the y-intercept is 0. So we can again start at 0, but this time to get to the next point on the line, we would go rise over run, down 1, and left 1. Or it should be right, excuse me, lefts and rights. Down 1 over 1, down 1 over 1. And we could kind of see that if we were to connect our graph, it would be a line with a negative slope. So at this point, I'll pull my domain in one last time, and it's reminding me that the domain is x values that are less than 0. So in other words, I'm looking at negative x values. So if I'm looking at the x-axis, it would be values to the left of the origin. And so that's telling me to take the piece of the function for all those particular x values. So all negative x values, I want to take the corresponding function piece. So it looks like we would erase the part where we had positive x values. And again, the domain always tells you where the cutoff point is for the particular x value. So in our idea is it's cutting off at x equals 0. But if we were trying to mark the edge of the function, that would be an open circle based on our inequality symbol. When there's not an equal to symbol underneath the inequality symbol, that particular x value is not included. Now, if we're going to transpose that onto our formal graph, we're going to see, even if we did make the open circle, it got closed by the piece on the right side. So I won't even put that there. I can now use, and I'll draw it maybe a slightly different color just so it kind of helps us with this. Again, we're looking at this side of the function. And remember, it goes on and on forever. So when I look at this a little closer, I mean, I see the piecewise function, but this reminds me of a famous function that I've been dealing with since maybe pre-calculus or maybe a little intermediate algebra. It's actually a little disguise. This is actually the absolute value function. Remember, the absolute value function is enclosed in bars. So one might say, you know, why didn't you just define it as f of x equals absolute value of x? And yeah, that's a great question. But I believe what we're trying to do is we're planting the seed in your mind, because eventually if we start dealing with limits and the absolute value function comes up, we tend to like to focus it on when we do see two pieces, a piece where we have a line with a positive slope, a piece where we have a line with a negative slope. So kind of keep that in the back of your mind until we get on to limits a little later in the chapter. We'll kind of revisit this again. Just to kind of make sure, once I'm kind of done with this particular picture, I just want to make sure I addressed everything in the directions. So one more time, we sketch the graph. And then we want us to find, the domain and range. So what I want to do when I find the domain and range is the same thing I was dealing with an example 1. If I want to address what the domain is, I believe I'll write it on to the right of this. What I'd like to do is I'm going to inspect the x-axis. And when I look at the x-axis, I'll kind of picture myself traveling along. Let's see, I'll draw myself purple. And I kind of go to the very far edge of my picture. So in my case, it looks like it's x is -5. And I just look to see if I have a picture above or below. In this case, I have a picture that's above. And anything that's happening at -5, it looks like the behavior of this function, it might happen at -10, or maybe -100 or -infinity. So it kind of looks like I have a picture for all of the x values from -infinity, using a little interval notation there. And if I keep traveling along the x-axis, I keep seeing, oh yeah, I have a particular y value for every single x value, decimal, fraction, or integer. I notice when I get to x equals 0, I have a picture that's on the x-axis, so that's valid. So I can keep going. And so I keep traveling and I see, oh yeah, there's picture, a y value for every positive x value. So this is helping me determine, and I'm going to the far edge of my picture or my coordinate system that's labeled, that's x equals 5. I see I have a value. So I can probably assume that I'm going to have a value somewhere at x equals 10, x equals 20, x equals 1,000,000. So it appears that the domain of this function considers all values of x from negative infinity to positive infinity are going to give you a picture. So I'll do the same. Do the same on the, oops, I did not want to erase the entire function. There we go. I'll erase a little bit from there. Okay, so I'm going to do the same thing with the range. Let's see, I'll try to do that in green, just kind of color code a little bit. I'm going to want to look at the y-axis. And when I'm looking at the y-axis, you will again see me kind of travel along the y-axis. This time I'm green. And I kind of start at the very lowest y value I see in the coordinate system. In this case, it's -5. And I am looking for a picture to the left and to the right of that value. And I notice I do not see a picture. So that kind of implies if I were to go to -10, would I see a picture to the left or to the right? I would not. And so that implies that I'm not seeing any pictures until, let's see, I'm going to keep traveling upwards, and I don't have to just stick with the integers. I am looking at decimals and fractions. But it appears at y equals 0. That is the first time I see a picture or a representation of my function. So I'm going to have the range start at 0. And there's no hole or anything strange happening at this point other than that it's a corner. But it does indicate that the 0 is included, so I'm going to use a bracket. And if I keep traveling along the y-axis, I'm seeing that there's x values for every particular y value I address. And even at the far end of the y-axis, at least the way the coordinate system has been drawn, I notice that there's a picture to the left and to the right still. So that's probably going to happen because it happens at 5. In this case, it's happening at 10, 20, 1,000,000, infinity. And that's just kind of the behavior. A little bit of studies from our past, we kind of know these absolute value functions, they do go on forever and ever in the positive direction, assuming that we're not reflecting. So my range for this would be 0 to infinity. So we'll have a chance to inspect this a little bit more. We're going to be dealing with, when I'm going to bring this up in a few minutes, the parent function toolkit, a little bit reminder of all the graphs we've ever studied from our algebra and trig classes. So now moving on to example 3, another one that we kind of come across, and maybe we didn't have as much of a chance to study it. I'm going to erase this so that you can see the function. And unfortunately, sometimes when I draw a PDF, the full function doesn't come through. So I'll make sure if this were a quiz or exam, I'll be very clear. We actually should see there are kind of double brackets around this particular x, and I'll draw it a little bit prettier for you. So when you kind of see this notation, sometimes people draw a bracket. So an X, a bracket, and they'll kind of do like a double mark to help them. That is actually defined as the greatest integer that is less than or equal to X. So it's a little more complicated than an absolute value function. A lot of times when you plug in values to the absolute function, value function, you're saying, okay, you know, if I were to talk about what is f of -2, we would write it where we're plugging in the -2. And those absolute value bars would be defined as the distance from -2 to 0. And the reason why it always comes out positive is because distances are always positive. So that's kind of the math operation we use when we're evaluating an absolute value function. But the greatest integer function gets a little bit more confusing because there's a lot of things going on in the graph. It's a pretty graph, but we have to kind of analyze what this means before we actually start playing with the graph. So I like to do this on a number line. So I'm going to pull up a number line. I'll just draw a number line for myself. And we'll kind of test out a few together just to make sure. I'll start very nicely. 0, 1, 2, 3. And then I'll go negative. 1, 2, 3. Trying to keep the same uniform distance when I graph by hand. And so if we were to kind of ask you a little bit of math notation, if we said greatest integer, if we're dealing with 2.5, what I'd like to do is I'll mark where 2.5 is on the number line, just so I can understand what's happening. So that's about here. And I'll draw it above just because I don't have as much room here. And what it says is if you land in between two integers, you're always going to look at the fact that the definition is it's less than or equal to that particular value. So what they're trying to tell us is if you land in between, you're always going to round down. And the greatest integer that is less than or equal to 2.5 is actually 2. So this would be the evaluation of that part. So we always look at returning an integer. I think I'll write this. Greatest integer always returns an integer back to you. And we always round down. And I like to emphasize when you round down, you're actually looking to the left. Sometimes it gets a little bit shaky if we're dealing with negative numbers. Just kind of we're not as comfortable sometimes with that. So if I can kind of keep that in mind, I'll go with it. So for example, we'll do another one together. Let's look at, I'll look at 0.3, greatest integer of 0.3. And I like to mark it down. So 0.3 falls in between 0 and 1, a little bit closer to the 0. And again, if you're going to round down, it's going to go to the 0. Now, want to play with a few more just to make sure you have it, and then we'll talk about making a table for this. Let's look at sometimes when we have negative numbers. That could give us a little trick there. So let's go with, I'll go orange this time. If I saw something like negative 2.1, I'll go where negative 2 is, and I'll kind of mark where I think negative 2.1 should be. It's not quite to scale. So if we're looking at the greatest integer, remember it's always less than or equal to that value, so we are always going to round down. So that would tell us that we would be pushing ourselves to using a negative 3. So it doesn't matter when we're not really looking at rounding rules. I know you guys are looking at, for example, I'll play with a negative number, running out of colors here. I think I can do another blue one. If I had something like a 1.9. Now, a lot of times people think if you were rounding, yeah, it'd be close to 2. But the definition of the greatest integer function is we can mark where it's located, and yes, it's close to 2, but it means that we have to look at the value that's the integer that's less than or equal to it. So that would indicate that we round down, so that number would be a 1. So just be careful. when you're looking at this. And a reminder is sometimes we don't have to see decimals or fractions in this greatest integer version. One more example, if I have, what's the greatest integer of -3? Well, if you mark where -3 is, you're right on the integer, so you could just choose what that integer is. So kind of be careful. If we were to kind of play with a table to get the idea of what these look like, another representation of the function. It's going to help us get an idea. An XY chart. I am running off the paper a little bit, but luckily we have plenty of it. I can talk about X and then the Y value being the greatest integer function at X. We can play around with the first few and then we'll start to get the idea that if we go with 0, the greatest integer of 0 is 0. If we're looking at 0.5, the way the number line would work is we'd be looking at what's in between 0 and 1, so we would round down to 0 as well. 0.2, same idea. 0.9, same idea. If we were talking about the number 1, that we're right on the integer, so we can just take it as is. But if we have 1.1, we're dealing with 1. And you could kind of continue to do this until you get the idea, but the way that looks, and this would be kind of me looking at maybe a portion of the graph. If I look in between 0 and 1, no matter what X value I choose, I'm always going to round down to the integer. So you kind of see that there's always the left side gets a closed circle and the right side gets an open circle, and then we use a line to help us. Now I did exaggerate that open circle a bit just to help you. So when you land in between, you're always rounding down to the integer. And you can justify this as well. If we were looking at the next piece, we can also write coming from, if we're starting at 1, we would have 1, 1. But if we have 1.1, we're rounding down. If we have 1.5, we're rounding down, and we're looking at another copy of this open circle, closed circle business. And actually, a few more of these, I'll make them a little bit prettier. You're going to see that there's a pattern happening. So we kind of like this one. It's pretty. Here we go. Here we go. And I can continue in the other direction as well. So notice it's an open circle on the right, closed circle on the left, because we are rounding down. And if I go through my rest of my graph, I think I'd have a closed circle at the very top. And so a lot of times when people see this pattern, they kind of look at it and they're like, ah, yeah, it's also known as a step function in some sort of way. So sometimes people refer to this as a step function. Kind of looks like stairs. And if we're actually looking at the domain and range of this, I'll kind of help you out a little bit more on here. The domain, actually, if you travel from left to right on your x-axis, it appears through the entire function that the domain is actually all real numbers, negative infinity to positive infinity. Even when you see these holes or open circles, let's say you're at x equals -1. Yes, there's an open circle at y equals -2, but there is a closed circle at y equals -1. So that's kind of describing why these numbers get covered. So now we have the range. If we kind of think about what the definition was, the range talks about, again, greatest integer. The range, if I can describe it in English, sometimes that's a little easier for us too. It's the set of all integers. If you want to make it a little bit more fancy, a little set notation, we could say range only has y such that y is an integer. Or if we want to make it a little prettier, sometimes mathematicians don't like a lot of writing. We use the set z, or we call it fancy z, to stand for the set of integers. And let me, instead of writing the is, I will take care of this. So I will look at the element right here. So y such that y is an element in the integers. And what's going on here is we really wouldn't be needing to talk about interval notation for problems like this. So don't stress out too much. So that is the greatest integer function. And I like to kind of pull out the calculator, the TI for us one more time. So if we're looking at the picture right here, I can pull up my TI for you. I'm going to share this with you. And just to kind of start us off, we'll warm up on the TI. If you want to type in absolute value and greatest integer function, we end up seeing that in the math menu. So we're going to go into math. That's the math key on the far left. And I will press the right arrow key to number. And here you will see the words ABS, or letters ABS, and that stands for our absolute value. Now, sometimes, depending on what type of TI you have, the absolute value doesn't always show up as bars. They might use the same letters again. So not to worry, we still get the same picture no matter what. So I have the absolute value of X. And if I were to press graph, you will see it's behaving exactly how we graphed it as well. So that's a very nice way to confirm if we're ever trying to graph something by hand. What are we looking at? Also, if you're looking at order pairs, you can, a lot of times you can play with the table. You press second graph, it'll pull up the table, and I have my table set up on, I'll show you just in case. I have my table set up so that the independent variable, that's the X value in our case, is set up on ask, and the dependent variable is on auto. So that allows us, if we're wanting to find particular values, we can type in them to the TI, and it will tell us X value versus corresponding Y value. So it's kind of nice to see. Now, if I were looking at my picture, my graph, if I were wanting to look at the greatest integer function, I'm going to go back. I'm going to erase my Y1 again. And I'm going to look at how to type that in. And so that's not so obvious. We don't really use it too much from our pre-calc classes. So I'm going to go back. It's kind of, anytime I'm kind of lost, the math menu always helps me. I'm going to scroll over to the number, and the greatest integer function, in our case, it's going to be number 5. And I know this one doesn't even show the fancy double brackets, so kind of we're all in the same plane here. So I have integer, greatest integer of X. If I were to press graph, oh, so pretty. So you could kind of see like, oh yeah, it makes the steps. The only thing with the TI is that sometimes it doesn't, or most of the time, it doesn't tell you what the endpoints look like. So if you were to just give this graph on a test or mark it on a test, you would need to really indicate where it's coming from. And so let's see if I can share with you all. I'll look for it. It's going to do this. Let's see. Sometimes it doesn't let me, but I'll try one more time. Here we go. I'll paste that right onto our lecture notes, showing this so you guys can see. And I want to make it a little bit larger so that we can draw on it Love this technology. So we can make it a little bit prettier for playing with the TI. But again, I would like to emphasize that the TI doesn't always tell us what the endpoints are. So if you were graphing this by hand, you would have to draw them all in. And that's not too fun. So you're kind of probably guessing that you probably won't get that sort of problem. We have other things to deal with, but you'd have to continue to draw all of these closed circle on the left, open circle on the right to get a full accurate graph. So that's the greatest integer function. They have also, there's functions as well. It's not just the greatest. We have something called the least integer function where the circles are flipped around. It'd be closed circle on the right and open circle on the left. You may see those more often in your everyday lives. If you guys ever try to mail packages, sometimes what happens is like a certain weight. If you're below 1 pound, you're always paying a set price. But the minute you go over 1 pound, even if it's just by a half an ounce, you're going to move on to the next pound up. So there's applications to these all the time. Also data plans, I think, in cell phones tend to follow the same format. So applications to the real world, always really neat to see them coming to life. And just kind of to tie up these two functions that we were dealing with, a lot of times you're going to hear us in the next sections talk about like what's continuous and how do we know if something's continuous. And the easiest way I can tell if something is continuous, I like to see the actual picture of the graph. One of the kind of nicest definitions I can think of is if you are a continuous function, you're able to trace the function without lifting your pencil or pen or whatever writing utensil you are using. There'll be a more formal definition to come, but at this point, if we're trying to decide which one is continuous out of example 2 or example 3, I'm looking at the absolute value function. If I were to trace, I'll use a highlighter, it doesn't appear that I have to lift up my pencil to actually draw the entire function. So that would indicate that example 2 is continuous. The function absolute value of x. If you were trying to play with the greatest integer function, you'll notice that if you're starting on one piece, you can highlight it, but then if you want to get to the next piece, you have to lift up your pencil to get there. Subtle, but it's kind of a very nice definition to start off the class with. So now, if we want to just inspect functions a little more, I'm going to encourage, I included this in your files, I encourage you to look at the parent function toolkit and see if you can graph these. Parent functions for the most part are on the left side. And sometimes reflections, shifts, translations, or sometimes they call them transformations, are on the right side. I encourage you to look through this and review through it. It's kind of something that will help you throughout the class to recognize behaviors of functions. So I'm not going to cover that too much in depth. I know that you definitely can look at the e-text on some videos to help you out with some of that if you've forgotten it along the way. But definitely you'll be responsible for this. So make sure you download it and work on it a little bit just so that you have a nice clear idea of what it means when you have negatives or different numbers within your function. So almost set with section 1.1. We have a little bit of algebra, some analytical work to do. Well, everything's algebra in this chapter. We're going to review what it means when we're talking about symmetry. So I'll give you the definition to help you out with that. If we're talking about an even function, an odd function, what kind of comes to my mind is a lot of trig functions from our past. We could deal with that in a second, maybe even using the TI. But I'm looking at the even function being defined as if you were to plug in a negative x into your function and simplify it, you would end up getting the original function back for all x in the domain of your function. And a lot of times, just kind of getting you situated with maybe higher level math class, sometimes when we use the words for all, it's so common, you will see us use another notation. It looks like an upside down capital A. So if you see that, that's what they're trying to describe. And a lot of times, if we're looking at symmetry in even functions, they kind of go hand in hand. Even functions are symmetric about the y-axis. And so examples of this one, and I'll pull up the TI to help you guys see this. We have f of x equals x squared, a parabola for us. Or even we could pull up our trig function, g of x equals cosine x, just changing the name. If we were to pull up the TI, let's see if we can do that. I'll graph that really quick. I'll do trig, just because it's not bad to continuously review our trig. And I know I'm on a standard window, so I always like to maybe go from I'll go from negative 2 pi to positive 2 pi. And then I'll make the x scale like our past. We'll do pi over 2, just because things will come out prettier that way. And mathematicians, we like everything neat and organized for the most part. My y min, y max, I'll kind of keep them. I know that their max and mins are at 2, but I'll go, 1, but I want to kind of show a little bit higher of the graph. So here, let me go back. Sometimes when I talk and type at the same time, there it is, that window. I can't have the same y min as the y max. Here we go. So we see we have our nice little wave. It's the cosine function. See if I can capture that on the screen for you so that we can kind of inspect this. I'm going to copy that over to our OneNote, and I'll paste it over to the right side. Now I'll expand it a little bit because it's good for us to view. Here we go. Just a little bit larger. There we go. So if we were looking at this definition, anytime they talk about plugging in negative x, we want to see the particular y value coming back into play. So what they're trying to say is, if you do see, let me see if I can plug in what's happening at pi right here. So if we were to plug in g of pi, that's cosine of pi, on the function, we get -1. So that value, we have pi -1, or if you're saying pi and g of pi. So what this definition is trying to tell us is, if you were then to plug in -pi into your function, so that's over here. See if I can write that down in red. It should have the same value as its positive counterpart on the x-axis. And so we do see, aha, for every function value, whether the x value is positive or negative, they will have the same values. So remind ourselves, cosine of pi is equal to -1, as is cosine of negative pi. So it's just kind of a visual to help us out. But a better visual, if we're not inspecting everything point by point, if we're looking at even functions, the key is that they are symmetric about the y-axis. So that's going to be a little bit of a more of a giveaway. So if we were looking at the y-axis and we were to fold along the y-axis, we can see that the left side will match up with the right side. So that's kind of a nicer giveaway for all of us. But I know we're going to have to deal with a little bit of analytical work in example 4. So I want to kind of review with that particular notation. And I think you might have played with trig functions before, a lot of in your identities, just to kind of pull cosine back at us. If you talk about a cosine of -x, it's the same value as cosine x. One of those identities come back to us. That's where the definition of the even function comes into. So I like to pull that up into play. So you're probably guessing if we're going to talk about even functions, we're going to talk about odd functions. And the difference between an even and an odd function is you will see, let me see if I can erase a little bit, leaving ourselves room. Sometimes I get carried away with all my writing. Don't leave room for the rest of it, but we fit it in as we go. If we're going to look at odd functions, we're going to define odd functions. If you plug in a -x, what happens when you simplify, you will get the opposite of your original function for all x in the domain of f. And odd functions are also known as symmetric about not the x-axis, that would not be a function, it's symmetric about the origin. Sometimes we're so used to making guesses, but. And so an example for that, a little bit of algebra, one of the ones that come into mind algebraically, we have x cubed. Or if I were to play with maybe a trig function one more time, the sine function comes back to me. So if I can show you that, we will be in good shape. Let's go and pull that up on our TI, see if we can kind of inspect it. That's my old version. Let's type in sine of x this time. Graph this and we can kind of see, oh, there's similarity. I'll take a screenshot of that so we can draw on it. And I'll paste it right below our cosine function. Enlarge that for you so we can all see. There we go. And the reminders that that's y equals sine of x if we were going through this. And symmetry about the origin has sort of like a little twist through the origin. So you kind of notice that you can't fold along the axis exactly to match up, but there's some sort of relationship. What I'd like to do, this is kind of where the particular values come into play. I'd like to kind of talk about what happens if we, let's deal with the same pi over 2. That might be kind of a nice idea. Okay, so if we were to talk about what is the function evaluated at negative pi over 2, that's g of negative pi over 2. We would kind of remind ourselves, okay, sine of negative pi over 2, we're going to see that it is -1. Now, if we look at the comparison We're trying to understand what is this relationship. If we look at the sine of pi over 2. Okay, so bear with me for a second. The sine of pi over 2, I'm sorry, that's a g function. I should be a little bit more careful with my notation. Okay, so the function evaluated at pi over 2, that sine of pi over 2, that's actually equal to positive 1. So what they're trying to tell you is that if you have a y value on the function, its opposite y value will also be on the function. So you could kind of see like, oh, well, that's not the same thing. They are the same distance-wise from the x-axis, but they're in different positions. So this is where they're talking about, if we're looking at our definition, if we were to play around, we can say, okay, g of -2, pi over 2, excuse me, that's not quite the same as g of pi over 2, but it's the same as its opposite. So if we were to take the opposite of positive 1, we would get -1. It's a little bit of inspection to go with. Sometimes you don't necessarily need to go through all of them and inspect them, but it's nice to kind of use the trig functions. I do remember a very nice identity of whenever you had the sign of a negative argument, they said, oh, you're allowed to pull the negative sign out and take the sign of the actual positive value. That has to do with the fact that it's an odd function. So that's kind of where it's coming from. So you might want to kind of utilize that if we're playing with some of the trig functions later. So even and oddness, inspecting graphs, that's kind of help us out. Just coming up with some concrete examples definitely helps me observe some of the properties a little bit better than if I were to just memorize these random facts. The last part with even and odd functions, I want to make sure that we actually have an analytical way to prove them, because sometimes, you know, you might not be able to use your TI in some of these classes. So you're going to have some sort of way to prove it without having to draw a graph. And sometimes the graphs are too complicated to draw by hand. So this is where we get into the analytical part, a little bit of pre-calculus coming back for us. And example 4 is asking us if we are even, odd, or neither. So when they're asking this, sometimes you can graph it and see what's going on, but there's an analytical way to prove it. And analytical is just fancy for doing this by hand and using properties. The first thing you would always go back to is the definition. So if they're asking for even or odd, you just have to think, okay, in both cases, in an even or odd function, they're always telling you that if you plug in -x for x, they want to figure out what do you get once you do the simplification. So my first step for showing this is always saying, okay, let's plug in f of -x to our original function. So if we were to do that, and I will draw a line so that we're not going through all of the old work. I'm going to look at plugging in -x wherever I see x in the original function. So here I have a negative sign of -x. And then at the denominator, I've got 5 -x to the 4th plus 3 times -x squared. And then plus a 4. Here we go. So I plug in -x wherever I see x in the original function. So just kind of refreshing that for you all. And then you go through a little bit of algebra to simplify. So what I want to look at is if I were to actually find what is the value of 2 times -x, I would have -2x minus Now, this is where we go into a little bit of the evenness or oddness. We do know already that sine is an odd function. So sine of negative x is the same as the opposite of sine of x. And another little bit of math we pull from our past is whenever we have negative numbers raised to even powers, they're going to come out as the positive version. So negative x to the fourth power will be still x to the fourth. So we'll still have the 5 in there. There'll be a plus. Negative x squared will come out to positive x squared. That's negative x. You don't want to show it on the side maybe. Negative x squared is the same thing as negative x times negative x, which gives us positive x squared. Just to kind of refresh our memories. And don't forget that there was a 4 there that we didn't plug anything into. It didn't have an x to begin with. So once we do the simplification, a little bit of math. Oh, don't forget, we're subtracting a negative. So that means we're actually adding. We have 5x to the fourth plus 3x squared plus 4. What I like to do is I like to compare back to the original function. So I'm going to take this piece right here, and I know I'm drawing a little bit more lines, but I do like to compare. If I see that they're exactly the same, without doing any sort of math, I can stop right there, because then you would know that if you plug in negative x for x and you get back the original function, you actually have an even function. But if I look at this closely, if I'm comparing all my terms, I do have the same terms, that's not going to change, but there's always like some issues with the signs. So I'm noticing right away that I do not see the exact same function coming back at me. Before I make a decision to say, hey, it's not even, or hey, it's odd, I want to kind of play around, especially with these rational sorts of functions. Well, rational-like functions, I'll say. I'd like to inspect a little bit more by playing with factoring out negative signs to see what I can really come up with. So I'll erase this for a little bit. And a lot of times what I like to do is I kind of look at, well, it appears that my denominators are already the same. So they kind of differ by the sign in the numerator. So this kind of gives me a clue where I could say, well, let's see if we could factor out a negative sign to kind of make it look like something that would be a little bit more in line with our definition. So if I factor out a negative, that would leave me with a positive 2x minus sine x all over 5x to the fourth plus 3x squared plus 4. And then if we kind of see this right away, I'll notice that, okay, let's compare it back to the original function one more time. I see that the denominators has not changed. We did not do anything to the denominator, but now the numerator looks the same. And what the issue is we have a negative sign on the outside. So what I'm actually looking at, this whole piece right here, see if I can use a little bit of color. This whole chunk right here is really just the original function, but what's there is negative f of x. So what we've done is we've done a little bit of math to show, so just kind of a little bit of rehash. Okay, so we have shown f of negative x equals negative f of x. And for that reason, if we've done that, we can then say f of x is odd. That's you justifying your work. It's your first proof of the math class for this semester. So, oh, I should kind of point out also, another shorthand mathematician stuff. That part is also, when you see the 3 dots kind of in a triangle, that is shorthand for therefore. Feel free to use that, or you can just use so or therefore. So kind of whenever we do proofs in this class, which we will be seeing a little bit, we always like to show definitions. So you kind of see if we're looking at definitions of even and odd, the first thing we ended up doing is we tried to show, okay, let's look at computing f of negative x. We did have to do some algebraic manipulation to play around, but we ended up getting a result. We ended up showing that f of negative x was equal to negative f of x. And since that is the case, you can make your conclusion based on the definition that you have an odd function. So a little bit of practice with that. You'll have a nice time when you do WebAssign. You'll get a bunch of different functions to play with on that. It's a lot. This is a lot of pre-calc in one section. It was pretty much maybe 6 or 7 weeks of all of this in one nice compact lecture. So one last situation, a couple of situations in the section 1.1, kind of throwing a bunch of math topics at you, but it does go along the same lines of function notation. We're going to revisit the difference quotient. And the difference quotient is defined by this formula. We have the function evaluated at a plus h minus the function evaluated at a all over h. And just so that we can see this put into play, because sometimes it doesn't really make sense unless we actually provide some application of what does this really mean. We're actually looking at a random function that kind of looks like to me a half a parabola in my particular example. And what I want to do is kind of demonstrate that I'm selecting maybe a location on the x-axis somewhat close to the origin. So that's my A. And if I look at a x value a little bit to the right, I'll make it further apart to make an exaggeration. I have a plus h. The reason being is that you are h distance away from each other. So a, then add h, and you have a plus h value. Now, if we do this, and I kind of jumped a little bit, so used to when I find an x value, what's the corresponding y value? But for these particular x values that I've chosen, I draw a vertical line, or my eyes draw a vertical line. Not part of the graph, but just an idea. And I draw to where the location is, where's the corresponding y value based on this particular two x values. So a, we end up having f of a. We don't really know the value, but it is the function evaluated at a. And then a plus h, if we were to name the particular y value, we'd have to go map ourselves back to the y-axis and say, okay, that's whatever number that is. In our case, it's f of a plus h. And once we kind of locate those 2 points, we don't really know their numerical values, we know their generic values. What we can do is those 2 points, if we were to draw a straight line through them, I'll do the best I can. And it's okay. I prefer rulers, but we'll go with it. We have ourselves a line. And whenever you draw a line through a function, and it's actually passing through 2 points, maybe we haven't defined it so much, but I'll just kind of either define it now or maybe refresh your memory. This line right here is what we call a secant line. Not to be confused with the trig secant function. And the definition of a secant line is it intersects the graph in exactly 2 points. We do have it, we see it. Oh yeah, exactly 2 points, a plus h and f of a. And so what I like to do is pull back some prior knowledge. If you guys can remind me, Oh, you're not here. Just remind me that if we're talking about slope of a line through 2 points, let's bring that back to the front of our minds. I know we used to talk about slope as m. And what happens is if we're looking at the 2 points, a lot of times they talked about the 2 points as x1. Let me see if I can give myself a little more room. x1, y1, and x2, y2, just to kind of remind ourselves that they are 2 distinct points, 2 different points, as we do have. So just kind of a reminder, if we had that formula, the slope would be the differences of the y's over the differences of the x. Really talk about rise over run. And the way I see it, if I'm actually going to relate this to my generic drawing that I have right here, instead of x1, y1, see if I can map this a little bit better. If we were trying to relate our function notation, in our case, we had a comma f of a. F of a, so we want to look at. And the other point, the second point on the line, if we're looking at x2, y2, just a distinct point, we are looking at a plus h, comma, f of a plus h. So really what we're looking at is who are the x values and who are the y values of these 2 points we have defined with such notation. And so if I was going to describe who is my y2 in this nice little formula, I'm going to have a y2. In my case, if I'm looking at the mapping, the way I see it is my y2 is the same thing as f of a plus h. There's a minus sign from the slope formula. My y1 is defined as f of a, same thing. So that's the f of a from the formula, y2 minus y1. And then over x2 minus x1. So if I kind of map those two as well, so x2 maps as a plus h. We'll keep the same color scheme for you. And f of a maps as just an a. So the x value of f of a is a. So the differences of the y values over the differences of the x values. If we simplify this just a little bit, I mean, we can't really do anything with the numerator because we don't really know what the function is. But we do know the denominators, the a's do cancel out, so we would have just an h. And that, my friends, we have just figured out how did we really come up with this difference quotient formula. Really, we kind of look back at it, it's a nice way to help us memorize it. It's really just the slope of the secant line. So that's kind of something really, really key. A lot of times when we're in these higher level math classes, there's a lot of formulas. It really helps to understand where they're coming from. If you can make a connection to your past, it's a little easier to build on that knowledge than it is to memorize just random letters and numbers everywhere. So one of the key points is that the difference quotient is really just the slope of the secant line. That's kind of a nice way to demonstrate relating to intermediate algebra versus calculus. I guess this was a little pre-calculus, but this is going to be a theme along the way. So keep this in your mind. We're going to revisit this a lot of times. So one last example to help you out with any of your homework. You may have some more complicated functions. They want us to practice finding the different quotient for particular functions. And a lot of times when I'm going along with the difference quotient, it's kind of a three-part process that involves you plugging in with algebra. So the first thing I always do for myself is write out what the difference quotient is. So if I can, I'll write it out over here. Difference quotient is defined as f of a plus h, subtract off the function evaluated at a, and it's all over h. And if we try to look at what we're dealing with, there are three parts. The first part would be evaluating at f of a plus h. So I can do this on the side. So I want to talk about function notation. And the second part would be kind of rewriting what is our f of a. And sometimes that part is a little easier to deal with first. So just kind of remembering with function notation, our original function is f of x equals x squared. That's what they're trying to have us refer to it. So if we had f of a, all that tells us to do is replace the x in the function with whatever is in the parentheses, the argument of your function, f of a. So f of x is x squared, so f of a would be a squared. Now, similarly, if we're looking at f of a plus h, what happens is we will do the same idea. Instead of just a single h, a plus h goes together. Remember, it's everything. That's why sometimes I say it fast, so we know that we cannot break up the a or the h. F of a plus h would be the same as us plugging in a plus h wherever we see x in the original function that they're referring to. So f of a plus h is a plus h squared, and f of a is a squared. Now, a lot of times what they prefer us to do before you start plugging it into the difference quotient, make your life easier. And let's say we can simplify a plus h squared first. And that's the square of a binomial. So just remember, there is a formula that allows you to go quickly, but it's just in case you forget. So I'm going to go back to your past and say, what does it mean to have an exponent? A plus h squared means you are multiplying a plus h out twice by itself. And whenever you are multiplying two binomials together, a lot of you guys think about it as FOIL. I think about it as distribution. I'd be looking at a times a, which is a squared, a times h, which is ah, h times a, and h times h squared. So we have an aha moment. A times h is the same as h times a, so we have ourselves like terms. So we have 2ah, two of those. I just wrote them in alphabetical order. But our final simplification of squaring that binomial is a squared plus 2ah plus h squared. And a lot of times, if you take care of that work on the side first, it makes this different quotient simplification a lot nicer for you. So I strongly recommend it, taking your time. It doesn't really benefit anyone to skip steps. It really just helps us remain accurate. So let's do that. Two pieces to the function. It's really the numerator you're dealing with. So f of a plus h, if I'm going to plug that in, let's make that a little nicer. Okay, so f of a plus h, that's going to leave us with a squared plus 2ah plus h squared. We're going to subtract off the f of a. So here, if we're subtracting off just one term, all we have to do is use the a squared. That is still all over h. So at this point, if you can, see if there's any combining like terms. Sometimes things cancel out, which we do see that the a squares neutralize. So we end up having 2ah plus h squared over h. Now, the very last thing to check for, especially when this is a quotient, it's very beneficial, and this will be utilized a lot in these next sections, if you have any common factors on the top, and I'm really more concerned about the h's. What I like to do is see if the h's will factor out. That's going to be the goal eventually. And it does look like in the numerator, the h's do cancel out. So we have, I'll write this out, 2a plus h. I factored out the h from the 2ah plus h squared. Got the remaining result. And a little bit of math for us. Anytime we have same factor over same factor, there's multiplication going on. This means we have the number 1. H divided by h is 1. That's why people can say they cancel. So your difference quotient in this case is 2a plus h. And I prefer going generic first. Saves me a little time with some of the extra math calculations. I'll show you an alternative way. Maybe if you ask me, maybe you should like double check, but I like this way a little bit better. Kind of keep in mind when I'm done with the problem, there's a lot of math going on. I always want to read the original directions and see if I've answered everything. And it asked me to find the difference quotient, but it's also got one little tag on it. It's asking me what happens when a equals 3. So the very last part of this particular problem, it would be me trying to understand what happens when a equals 3. So that just means I'll plug in that for a. Two times 3 plus h ends up getting 6 plus h. And that is the difference quotient for that particular example. F of x equals x squared when a equals 3. And the reason why I kind of like to keep with the generic version of finding f of a plus h and f of a is because those never change. When you start plugging in numbers for a, you start trying to do a little bit more multiplication, the numbers get a little higher. And of course, you're in calculus, you can handle it, but sometimes we like to save our brain power for some of the more in-depth thinking. So I kind of prefer to work with letters. That's just my preference. And then plug in a at the end when there's less math involved. 2 times 3 is a lot easier to compute than a lot of the FOIL problems. Now, just a sneak later, a little bit closer down the line, we're going to ask what happens when h gets closer to 0. So stay tuned for that. So at this point, this is our section 1.1. I'm signing off, wishing you all a great day. We'll touch base when we talk about section 1.2.